Hey guys, welcome to day 12 of programming every single day until I graduate. Um, Let me double check. Is it day 12? I think yesterday was day 11. Um, yeah. Yesterday I didn't do much coding because I was reading reading up on this kind of Haskell stuff, which isn't that entertaining. So I thought maybe should I continue reading it, or should I build a little mini game, like I don't know, like a super simple game, like tic tac toe, in Haskell, like something like this, so I can kind of code more. Um, I'm still not used to the um kind of um syntax to comfortably make something yet. So I don't know. Maybe I'll do this later, but this is a really long read, so trying to try my best to do it. Yeah, a lot to get through. Hopefully, I'll get to 4, maybe start 5, but I don't know. It's really hard to use kind of use this. I gotta definitely apply it because I usually just read a lot nowadays. In terms of the project, I might have to push that to next time, or next week, because I wanted to get input from like my mentor on some of the things I wanted to build. So I'll be talking to them next time. So once I get their input and see if I could um, kind of help define the scope of the things, I'll get to building it. But for now, do more schoolwork. I definitely need to read up on my operating system classes reading. Seems like a fun class. I'm really excited for it. Um, but yeah, let's just, I guess for today, um, today I'll just, I don't know, what should I do? I should just, yeah, today for today, I'll just keep reading up. Keep it simple. I don't want to, um, oops, I don't want to, oh wait, why'd I keep doing that? Learn Haskell. Okay. I'll probably, maybe today's the last time I record reading Haskell. But what else could I do? Maybe I'll do some of my operating system homework. I'm not sure. I'll see. I'll see. Let's see. Yeah, let's just get to reading. This chapter will cover some of Haskell's cool syntactic constructs. We'll start with pattern matching. Pattern matching consists of specifying patterns to which some data should conform, then checking if it does, and deconstructing the data according to those patterns. When defining functions, you can define separate bodies for different patterns. This leads to neat code that's simple and readable. Specific patterns to which data should conform. Okay, so kind of pattern matching stuff. You can pattern match any data type, numbers, character lists, tuples, etc. Let's make a trivial function that checks if a number we applied to it is a 7 or not. So what is this? We got, these are the class constraint, or not necessarily class, or like the type annotation or something like that. So we say it takes in an integral a and returns a string. when you call lucky, the okay, when you put 7, is there like that's interesting. Is there like an implicit equal when it's any other number? Oh wait, this is very interesting pattern. When you call lucky, the patterns will be checked from top to bottom, and when it conforms to a pattern, the corresponding function will be used. A number can conform to first pattern here is if it's 7. If it's not, falls to the second pattern, which means if it falls through, if it's not, it falls through the second pattern, which matches anything and binds it to x. The function could have implemented by using an if statement, but what if we wanted a function that says the number from 1 to 5 and says not between 1 and 5 or any number? Top to bottom, and when it conforms to a pattern, the corresponding function body will be used. It'll take a something, an integral. I forget what the integral type is. It'll return a string. The only way a number can conform to the first pattern here if it's 7. If it's not, it falls through the second pattern, which matches anything and binds it to x. This function could have been implemented by using an if statement, but what if we wanted a function that says from 1 to 5 not, and says not between 1 and 5 for any other numbers? Without pattern matching, we would have to make a convoluted if then else tree. That's pretty nice. With the last pattern, the catch on the top, people would say it would catch all the numbers, and then you wouldn't have a chance to filter. Okay, that the factorial function we implemented previously, we define the factorial of a number n as product 1 through n. We can also define a factorial function recursively. The way it is defined in mathematics, we can use this. We start by saying that the factorial of 0 is 1. That is super cool. Wow. This is like another kind of doing if statements here. Then we state that the factorial of any positive integer is that integer multiplied by the factorial of its predecessors. Here's how it looks translated in Haskell terms. If it's, so we kind of like this state it. What do we return for when it's 0, and what do we return for every other case? This is the first time we defined a function recursively. Recursion is important in Haskell as we take a look at it later. But in a nutshell, this is what happens if you try to get factorial of, say, 3. It tries to compute 3 times factorial 2. The factorial of 2 is 2 times factorial 1. So now we have 3 times 2 times factorial 1. Factorial 1 is 1 times factorial 0. So we have 3 times 1. Yeah. Now here comes the trick. We define the factorial of 0 to be just 1. And because it encounters that pattern before the catch-all 1, it just returns 1. So the final result is equivalent to 3 times 2 times 1 times 1. Had we written the previous, had we written the second pattern on the top of the first one, we catch all the numbers including 0, and our calculation would never terminate. That's why it's important when specifying patterns, and it's always best to specify the most specific ones first, then the more general ones later. Let's actually kind of apply this. Maybe we'll do fizzbuzz here, right? Oh my god, I keep learn Haskell. Let's do this. Rename this to fizz buzz. I want to see if I could do this. So let's call this fizz buzz, and takes an integer, I guess. Integer. It's like integer int a that does what? That returns a string, right? Hold on, I forget, is it camel case? Yeah, camel case. Are functions camel cases? Well, yeah, they're camel case. So let's do that. So I guess this is that's the return. Return type, what gets passed in. I don't need to say a variable, do I? So like for the case, it's like we define how could we do fizzbuzz? Could we put like a expression here? Or does it only can we do fizzbuzz with this or no? Could we put expressions here or no? Or is this only like a passed in? That sucks. I don't think I could do, because it's a bit more complicated. It takes in a number and it's like divisibility, right? Int like x. I think it's like mod. X mod 15, right? And then we say that equals let's see, so we could say, what is this called? This is fizzbuzz, right? And this is what is. I don't think this works. I'm just kind of guessing and toying around here. Like, so 5, and then 3. And then the last one is the catch-all. So what is the catch-all? It would have been the dx fizz. I'm not sure this is the right would this work, or is this a violation of what I'm trying to do? This is I don't think this works. It's kind of tweaking around, but I'm not sure. Yeah, I don't know. This is definitely, I don't think this works. Let's see if it breaks. Let's try to compile. Oh crap, this is bad. Like load the fizzbuzz. Yeah. It wouldn't make sense. You can't really put expressions here, right? But these are more like switch statements then, right? Essentially, kind of. But they're called like pattern matching. So, okay. And then try to call an input that we didn't expect. This is what happens. Commits a non-exhaustive pattern, and rightfully so. When making patterns, we should include a catch-all pattern so that our program doesn't crash if we get some unexpected input. Patterns matching can be used on tuples. What if we wanted to make a function that takes two vectors in a 2D space that are in the form of pairs and adds them together? To add the vectors, we add their components separately and their y components separately. Here's how we could have done it if we didn't know about pattern matching. Fs first B. Oh. We can take in two tuples and return that. Here we go. Much better. That this is already a catch-all pattern. That type of add vectors in both cases. So we're guaranteed to get two pairs as parameters. FST and SND extract the components of pairs. What about triples? Well, there's no provided functions that do that, but we can make our own. Well, there's no provided functions that do that, but we can make our own. First, second, third. That means the underscore means the same thing as it does in a list comparison. It means that we don't care about what the part is, we just write. Okay. Which reminds me, you can also pattern match in list comprehensions. Okay. Lists themselves can be used in pattern matching. You need to match with the empty list or any pattern that involves it, an empty list. But since 1, 2, 3 is syntactic sugar for 1, 2, 3, you can also use former pattern. A pattern like X will bind the head of the list to X and the rest of it to XS. Even there is only one element to XS and then being an empty list. Note that X and XS pattern is used a lot, especially the recursive functions. But the pattern in Gotcha. If you want to bind, say the first three elements to variables and the rest of the list to another variable, you can also use like It will only match against a list that have 3 elements or more. Now that we know how to pattern match against lists, let's make our own implementation of the head function. If it's an error, it can't call an empty list. Nice. Notice if you want, I forget what this apostrophe does. Like, I think it's like some kind of convention or something. So if you want to bind several variables, even if one of them is just take the x and return the okay. It causes the program to crash, so it's not good to use it too much. But calling head on an empty list doesn't make sense. Let's make a trivial function that tells us some of the first in inconvenient English form. Let's make a trivial function that tells us some of the first elements in the list in this. So it takes a show, and then if it's an empty list, do that. If it's the first element, this element has one element, show x. So it's just saying this thing has to be a part of the show type or something. And then xy, the list has 2 elements. This function is safe because it takes care of the empty list, a singleton list, a list with 2 elements, and a list with more than 2 elements. Note that the x and xy could be written as x and xy. We don't need the parentheses. Sorry about that. Remember our own length using list compression. Now we'll do that by pattern matching and a little bit of recursion. I forget this notation again. What does this notation do? 1, 2, 2. What does that do again? Oops. I forget what that does. What is that syntax? Now we'll do it by pattern matching and a little recursion. It's like some list or something. I forget that syntax. Always. So wait, what does this do? Like, L. 1, 2, 3. Is that a valid syntax here? I'm in the wrong project. To load FizzBuzz, I guess. Okay. What is that syntax again? I forget what that is. Is that like type notation or something? I don't know. This is getting difficult. We are implementing our own length function using list comparison. Now we'll do it by pattern matching and a little recursion. Similar to factorial function we wrote earlier, we first define the result of a known pair, the empty list. This is known as the edge condition. Then in the second pattern, we take the list apart by splitting into a head and tail. We set the length is equal to 1. Plus the length of the tail. We use this to match the head because we don't actually care what it is. Also note that the taking care of all powers and patterns of a list. I see. We call ham. Wait, so wait, what does that mean? What does this do? I don't get this syntax. It's getting annoying. I don't know what this freaking means. This, keep forgetting. There's a lot to retain. They're also called. These are also called as patterns. They're a way of breaking something up according to a pattern and binding it to names while keeping a reference to the whole thing. You can do that by putting a name and an at in front of a pattern. For instance, the pattern as XS. The pattern would match exactly the same thing as X. So is this like, what is this syntax? I forget, man. Like I don't remember any of this. I gotta go back. Is it types? I don't remember. I don't want to look through it. I might call it pretty early today. Kind of annoyed with this. Where am I? One more thing, you can use plus pattern pattern match. If you try the pattern match against xy plus ys, you would be in the first and what would be in the second list. Whereas patterns are a way of making sure a value conforms to some form and deconstructing it. Guards are a way of testing whether some property of a value are true or false. That sounds like a lot if an if statement, and it is very similar. The thing is that the guards are more readable when you have several conditions and play them really nicely with patterns. Instead of explaining their syntax, let's just dive into their Okay. You're supposedly normal. I bet you're ugly. Guards are indicated by pipes that follow a function's name and its parameter. Usually they're indented a bit to the right and lined up. A guard is basically a Boolean expression of value. Because it isn't, it falls to the next guard. So like a switch statement. So then these are like switched. Now I can do that fizz buzz thing. Let's try that. Fizz buzz equals. What's not equals? You gotta define the pattern of an integer int of, and it returns a string. So this just function will just return the corresponding number. So like, then we'll say fizz buzz x we put this here. That's a lot of spaces here. So here, let me say x. We could say the mod 15 equals 0. We return fizz buzz. Let me just do this. Oops. We say this to here, and this is 3. I think it's this, and then, or is it buzz? I forget I get the rules for the fizz buzz. Fizz buzz. So fizz is 3. Okay, so this is buzz. And then can we call, now we define the function, right? Can we now load a fizz buzz? Nice. So fizz buzz. Like this. Exception. Non-exhaustive patterns in. So this is wrong. Am I not allowed to apply that fizz buzzness here? Oh, we need to otherwise. Oh yeah. My bad. This is the case where there's no condition. Wait, is that a keyword? Otherwise? Okay. Otherwise, spring. Can we say like string? Is that how you typecast? I forget how to typecast. Like that? Crap. Oh, it's like show, I think. Oh, is it read? I think it's read. I'm not sure. I wish I remembered the year. I forget what the thing was. Is it read? Oh yeah, read. Yeah, I remember. So we say so read x, and we expect a string. Yeah. Oh, we can't do that. The hell? Is otherwise not a thing? What is otherwise? Is that a? Am I reading this wrong? Otherwise. If it evaluates the false, is otherwise. Otherwise is defined as simply as otherwise equals true and catches everything. This is very similar to patterns. Only check if input satisfies a pattern, but guards check for Boolean condition. If all the guards of a function evaluates to false, we haven't provided. I don't know why. Does this not work? Why is the compiler complaining here? Oh, let's read. Couldn't match type int to to character. Expected. Okay. Oh, I see. I guess character? But that's gonna violate. That's just the same thing, right? String. I guess we could say it like this then. Does that count? No, it doesn't count. I'm curious on what. I guess my types are wrong here. Should I say integer instead? Or is it character? Well, that's not true because these are all like all the. Or just, who cares? Just print this out. Return that x, right? And this should still be string. And then bruh, are you serious? What is going on here? Why am I running into this? I'm curious on what this is. Couldn't match int with character. Still the same. In the expression x, an equation for fizzbuzz. Yeah, that's true. It's not matching the. So into string, how do I do that? Into to string in Haskell. Convert into string. Should I say show? Show X. How does that work? Oh, nice. Okay. Then fizz buzz. 15. 20. Nice. Now could we do the? I don't know if there's loops. Have I learned loops yet? I don't know. But now I can do the. Is there? Did I learn loops yet? I don't think so. Is there loops here? I mean, I could do like I forget. I don't know. I don't think there's loops. Looping through a list in Haskell. I don't know if this, maybe we have to do it iterating. This is Python? Yeah, it's just, I don't know if I've ever iterated through anything. I think it's list comprehensions. I think there is. Yeah. So we can do this. Like apply a function. Yeah, we could do so like yeah, I got it now. Okay. X times, so we apply, let's call it I for element or index, or not index, L, Ellie, and just apply the fizz buzz on Ellie from pointing to 1 through 21. And I don't need any conditions, so this is good, right? Is that good? And then we'll see what L is. Okay, it doesn't work. Oh, no, I did it wrong. Define the what to do with the element and then call the what the element is coming from. Yeah, and then nice, and we can just print out L, right? Not L, S. Very nice. Is this correct? Wait, I want to see if LeetCode has that number. LeetCode FizzBuzz. Let me see if I can solve it in Haskell. This gets me in the mood for. Do you guys have Haskell? Never mind, I don't even have Haskell. Scala, Rust, Ruby, Dart, Go, Swift, PHP, Racket, Erlang, Elixir. So I guess this is the way to loop through stuff. Because I don't think I would have probably gone into loops already if there wasn't. No, right? But let's continue. So we did pattern matching. Guards are really nice. They're kind of better if statements. Very similar to switch statements. Not only that, we call infixes with backticks. We define them. Yeah. You can if you want to use it like that, you have to define it specifically. Where in the previous section? So let's see what where does. In the previous section, we defined BMI calculator and a berator like this. A berator? Oh, okay. Notice when we repeat ourselves 3 times. We repeat yourself 3 times. Repeating yourself 3 times while programming is. Since we repeat the same expression 3 times, it would be ideal if we just could calculate it once and bind it to the same name and then use that name of that expression. Okay. We put a keyword where after the guards, usually it's best to indent as much as possible. Okay, yep. These names are viable across the guards and give us an advantage of not having to repeat it. So if we decide that we want to calculate BMI a bit differently, we have to change it once. It also improves readability, giving names to things and make our progress much faster since stuff like our BMI variable here is calculated once. We could go a bit overboard and present our functions like this. Oh. This BMI is defined. Oh, I see. He defined what BMI means, and then he also defined what another variables are. The names you defined in. Okay, maybe I can actually apply this to our FizzBuzz here. I was thinking not, but what we have repeated here is what we have repeated here is probably the expression, but this expression is, I can't do much to that per se. I mean, I can say like I can say 5 and 3 equals. I guess I could do this, but I don't know if that's really clean, you know. I don't know if this is the correct way to do things. Just this is for 5. And well, 5. We'll just say 3. And then we can define them as 5 and 3. 5, 3. This is a really dumb. Oh wait, that's bad. Whoa. So 3 is here. I think here. I need a LSP for this. Yeah, I don't have auto format either. Let's install a matter of fact, since we're in it, let's install an auto formatter. Haskell. Let's just do a Mason. Haskell. Yeah, let's do that. Oh, I failed because GC cup canal. Wait, I need a Mason. Mason install. I mean, let's open up Mason. And what is this again? I don't know if I have GC cup. GAC cup. Yeah, I don't have this. GC cup install Arch Linux. GAC cup. If you use, oh, I can just install. Do I sudo pacman? So I got a sudo pacman. Okay. Yeah. So let's do sudo pacman. Haskell. Haskell language. Oh wow, it takes such a long time. I'll go back to the video when it finishes. Alright, I did some installing. I think I got the LSP working, I think, but I have to download some like compiler stuff, but we'll see. I think I might end this video soon. Just gotta figure out how to do this real quick. It says it's not in scope. Why could that be? I'm not sure. Please use spaces. I definitely should install a formatter because auto format. Haskell. I don't know the name. Let's look it up, Mason. let's look up, I think it's formatter, haskell formula, best formatters for haskell, ormalu. So ormalu, let's look at ormalu. Awesome. What's this? What's there? Oh Lord. Oh wait, I forgot why. Then I gotta got it. I got it. I'll fix it. Damn. So haskell. Let's say or how do you spell that? Ormo. What was the thing? This. And let's put this here. Whoa. Let's try it again. Fizzbuzz here. There you go. Nice. Now, will this compile, sir? Variable 9 scope. Yeah, I'm still getting that variable 9 scope thing. So, hold on. What would happen if I put this first one here? Oh, wait. I think 5. Yeah, I don't think this makes sense to do this, so I'm gonna x mod 15 and x mod 3 or 5, x mod 3. How come this doesn't run? Fizzbuzz. Oh, still. Why is the compiler complaining this time? Couldn't match expression. Oh. Whoa. I gotta say 0, right? It's a boolean. It's yeah. I think call it the day for today. After I fix this down, perhaps min function. Variable not in scope. Oh, damn! Is it that main thing I have to put? I know there was a. I have to put main or something. Let's call this main instead. Is that what it is? Okay. I think it's just I don't have like the main thing. It's just perhaps use min and put it from. Not in scope, whatever. um or could I just use this nice. Okay, I'm just using this as like a like I don't know really how to use like a whole function, like a whole thing to put as. Wait. Oh, is that how it works? Hold on. So do main input output. So this, now our hello.h file will look like this. I think that's somewhere, but I think, yeah, today is good enough. I'm gotta do some other homework. So, yeah, thanks for watching. I'll see you for day 12 tomorrow.